section 2.1. We're going to talk about relations first. So graphing, interpreting, and modeling relationships between two variables or two sets of data is an important goal for this course. Looking at the relationship between two variables. In our earlier work with graphing, we learned that two sets of data can be represented as an ordered pair, x comma y, and we can plot that so that we have a graphical interpretation. For example, suppose we select Jeff Green, Avery Bradley, Keith Bogans, and Gerald Wallace from the 2013 Celtics team, and we list their heights. They're 6'9", 6'2", 6'5", and 6'9". So we could write this correspondence between each player's name and their height as ordered pairs. So we could write Jeff Green, comma, 6 feet 9 inches. Avery Bradley, 6 feet 2 inches. So we write them as ordered pairs, right? So the set of ordered pairs is called a relation. That's just a mathematical definition. So a relation is any set of ordered pairs. Now the set of names, the x parts of the ordered pairs, the first entry in each ordered pair, is the set of inputs, and it's called the domain of the relation. So the set of names, Jeff Green, Avery Bradley, Keith, and Gerald, right? That set of names is called the domain of the relation. And the relation, remember, was the set of all the points, name, comma, height. Okay. The set of all heights, 6'9", 6'2", and 6'5", is called the range of the relation. So notice that 6'9" we listed only once in the range, even though it happened for two players. You don't need to list elements twice if they show up twice in the range. So this is just sort of like a little graphical picture. We have a domain, the set of names, the 4 Celtics players, and the range, the set of heights. And then I just drew arrows to say what goes with what, right? So Avery is 6 feet 2 inches. Jeff is 6 feet 9 inches. Gerald 6 feet 9 inches, and Keith 6 feet 5 inches. So it's just another graphical way of looking at a set of ordered pairs. So in these ordered pairs, we listed the name of the Celtics player first and the height second. But we could also represent this relation by switching them. I could put the heights first and the name second. So I would have 6'9", Jeff Green, 6'2", Avery Bradley, 6'5", Keith Bogans, and 6'9", Gerald Wallace. And I want to fill in the domain and the range. Okay, so my domain now is the set of all first coordinates, all the x's, the first entry in each point, which would be the heights, right? 6 feet 9 inches, 6 feet 2 inches, and 6 feet 5 inches. And I don't have to write the 6 feet 9 inches twice, just put it once. And then my range is the second, the y coordinate of each of these points. And those are the names: Jeff, Avery, Keith, and Gerald. Okay, and then I could draw arrows, right? I could do 6'9" goes to Jeff and Gerald, and the 6'2" goes to Avery, and the 6'5" goes with the Keith. Okay. Now, suppose in the award ceremony at the end of the season, right, we announce the MVP award goes to the player that is listed at 6 feet 9 inches. Who would get the award? Thank you. Because there are two players who are both 6 feet 9 inches. There's no way to tell who gets the MVP award. So this is an example of a relation that's not well defined. Okay, so if I give you an element of the domain, you can't tell which element of the range I'm talking about. So a function is an important special kind of relation. And our work in this course is going to focus mostly on functions which are well-defined relations. So a well-defined relation, or a function, has exactly one output value for any input value. So for each element in the domain, there is exactly one element in the range that corresponds to it. So in our basketball example, we have two relations, P and H. P gives the name as the input and the height as the output, and H gives the height as the input and the name as the output. So which set of ordered pairs is a function? Which one is well defined? B? Oh, P. Yeah, P. Yes, because each name corresponds to exactly one height. Yeah. So P is the function. Okay. And which set of ordered pairs is a relation? Close. Yeah, it's a little bit of a trick question. They're both relations. Right. Any set of ordered pairs is a relation. A function is a special kind of relation where each input corresponds to exactly one output. Question.
Why wouldn't A be H2?
Okay, so the problem was when we go back here and we look at when we define it as heights as input and names as output, it's not well defined because the 6-9 goes to two different names. Whereas when we defined it this way, that was fine. Each name has just one arrow coming from it, right? So this one is well defined. We call this one a function when each name corresponds to exactly one height. But when we do it the other way, each height doesn't correspond to exactly one name. Here's a height that corresponds to two different names. So that's what makes this not a function. Okay, so before we move on, so I have some typical non-math examples that I use to try to help you remember what's a function. So a telephone is an example of a function machine. So when you dial a phone number, what do you expect to happen on the other end of the line? It rings, and who's going to answer it? The one particular person you were calling. Each phone number corresponds to exactly one destination, right? So you know who's going to answer the phone. So each phone number goes to exactly one destination. So if pretend this is a phone number. If I dial 6-9 and I get Jeff sometimes and Gerald sometimes, that would be a terrible machine, right? So think of a function as a machine like a telephone, right? A function is a machine like a telephone. Each number has to correspond to exactly one thing. A television is also a good example of a function-like machine. You put in a number in your remote, right? You type in 22. What do you expect to see on the screen? The news channel, yeah, the 22 news, right? No. So you type in 22, you expect to always see what's on 22 is NBC, right? I think. Yeah. So you expect to always see NBC when you type 22 in. If sometimes you saw NBC and sometimes you saw something else, that would be a terrible machine, right? So that is not a function. It's not a well-defined function. All right, so now I'm going to have you try. I want you to determine whether each of these relations is a function and also find its domain and range. So I've got 4 examples there. 2 examples done with pictures and 2 with just ordered pairs. Okay, so let's go over it. So we have Phoebe, Amy, and Katie, and their heights listed on the right, right? So the domain is the names, range is the heights. Is it a function? Yes. So each name goes to exactly one height. If I give you a name, you can tell me what height they are without any confusion. So yes, this is a function. What's the domain of that function? Phoebe, Amy, and Katie. And what's the range? 5, 5, and 3, 1. Good. All right, how about this example where I have 0, 3, and -2, all going to 7. It's a function. Yeah, it is a function. So it's okay to have more than one input go to the same place. That's like it's okay to have 2 telephone numbers that go to the same person. What's not okay is if you have one telephone number going to 2 different people. So it's okay that the number 0, think of these as telephone numbers. Pretend if you press 0, you get person number 7 or something, right? So if you press 0, 3, -2, or 6, they all go to this same person. That's okay. The only time you would have a problem is if you press 0 and sometimes you get 7 and sometimes you get 13. Right? So this is a function. The domain is all these numbers on the left here, 0, 3, -2, and 6. And the range is just the number 7. All right, so now we have a set of ordered pairs, just a slightly different way of representing the function or relation, sorry. Is it a function? It is? Okay, so yeah, it looks like it is because my x values, -1, 0, 1, 2, 3. I don't have any repeating x values, so this is going to be a function. And my domain is -1, 0, 1, 2, and 3. And my range is all the y coordinates, 2, 3, and 5. And I just put them in numerical order because I'm fastidious like that. But you do not have to, no. Okay, next relation. Is it a function? No, why not? The input of 3. My 3 is in there twice. I have 2 inputs of 3, and sometimes I get 7. When I input 3, the output is 7 over here, and over here when I input 3, the output is -4. So if I said, tell me the output when the input is 3, you'd be confused. So this is not a function. Its domain is just the set of all x coordinates, which would be -4, -3, 1, and 3. Again, you don't have to repeat when you're listing domain and range. And my outputs, my range would be 2, 4, 5, 7, and -4. I missed that. It's okay. Yes, because every relation has a domain and a range, and a function is just a special kind of relation. Yeah. Okay, so how do you feel about it so far? Okay. All right, so now we're going to look at some graphs of relations and functions. So if our sets are real numbers as opposed to names and heights, but numbers to numbers, the domain and the range are both real numbers, we can use the graph of the ordered pairs to determine if we have a relation or a function. So again, the set of all x coordinates represents the domain and the y coordinates represents the range. So we want to use the domain and the range to determine if this is a function. So what is the domain of this function? -4, -2, 0, and 1. How did you come up with that list, Katrina? Those are the x coordinates of the 5 points. Wait, there's 5 points. Oh, I see. There's 2 at the same x value at 1. Okay. All right, what's the range? And those are the y coordinates of each of the 5 points, right? So is it a function? Why not? I have 2 points that have the same x coordinate and different y coordinates, right? So this point is at 1, -2, and this point is at 1, 4. So I have an input of 1 going to 2 different outputs. That makes it not a function. Is there some visual way you would be able to tell quickly? The vertical line test, yeah. So the fact that these 2 points lie on the same vertical line is what makes it not a function, because they have the same x coordinate of 1, but 2 different outputs. So they lie on the same vertical line, and that means it's not a function. So we call that the vertical line test. If any vertical line intersects a graph in more than one point, the graph does not represent a function. So this first example on the left is a function. I draw a bunch of vertical lines, or you can think of like sweeping a vertical line from left to right through the graph. It never touches the graph more than once, so this is a function. But this one is not a function, this one on the right, because I can draw a vertical line that touches in more than one place. Okay, here, here, and here. So if I want to use the vertical line test on these 3 graphs, is A a function? Yes. I can draw any vertical line, will never intersect more than once. How about B? Great. The open circle at the top. So really, I mean, any of these places seem fine, right? Anything to the right of 2 seems fine. It's this place at 2 that looks iffy. But because there's an open circle up here and a closed circle here, it only touches in one place. So this one is a function. How about C? Nope. Vertical line touches in 2 places, not a function. Okay, so most of the functions we're going to work with in this class are expressed as equations rather than as a set of ordered pairs. So in the very first lecture, we worked with this equation 4x squared plus 341x plus 3,194, and it represented the average cost of tuition and fees in public U.S. colleges, and x is years since the year 2000. So x is called the independent variable because it can be assigned any value from the domain. And the domain in this situation is any integer years after 2000. Plug in any number 0 to infinity. And then y is called the dependent variable because y depends on x. You plug the x in and you figure out what y is. So y depends on whatever x you plug in. So you find y after selecting a value for x. So our model defines a function since each value of x gives exactly one value of y. So to determine whether an equation represents a function, you have to solve the equation for y. So it has to look like y equals with a bunch of other stuff, x's on the other side. And if there are 2 or more values of y for a given x, then it's not a function. So let's look at A here. I want to solve it for y. So what would I do first? Subtract 3x. So I'd have negative 2y equals negative 12 minus 3x. Then what do I do? Divide by negative 2. So I end up with y equals 6 plus 3 halves x. I just divided the negative 2 into both of my terms there. All right, what do I get for y if I plug a 0 in for x? What do I get if I plug 1 in? It's not that complicated. 7.5, good. What if I plug in 2? 9. So it seems like when I'm plugging in an x, how many y's am I getting as the answer? 1. So this is a function. So you could make a little xy chart and just pick a few values and make sure you're only getting 1 y as your output. So when I plug in 0, I get 6. When I plug in 2, I get 9. And if I plugged in 4, I would get 12. Right? So only 1 y means function. Okay. FCN is my my personal abbreviation for function. Yeah.
Is it in that graph there ever goes with 2y's?
Not in that particular graph, no. So we just did 3 examples just to convince ourselves that there would never be 2 y's. Yeah. So I want you to, in your groups, look at B, solve it for y, and determine if it's a function. So I want to solve this equation for y. So I'm going to subtract the x squared from both sides. So I have y squared equals 16 minus x squared. So how do you undo squaring something? You square root. Okay, so I take the square root of both sides. And what is the square root of y squared? The absolute value of y. Absolute value of y. What is the square root of 16 minus x squared? Yeah. I'm trying to trick you into saying 4 minus x, but it is not. It's just, we can't simplify it. Okay, so let me explain why. I'll do it on a different slide here. So 16 minus x squared square rooted. If you let x be, say, 1, right? Then I would do the square root of 16 minus 1 squared, which would be square root of 15. But if I did if I wrote that as the square root of 16 minus the square root of 1 squared, I would get 4 minus 1, which is 3. And the square root of 15 is not 3. So the order of operations says you have to do what's inside here before you can square root. And since I can't do anything to 16 minus x squared, I can't square root. Does that make sense? So I have to just leave it as the square root of 16 minus x squared. So if the absolute value of y is equal to the square root of that stuff, then that means y itself is either positive or negative, the square root of 16 minus x squared. Yes?
Why couldn't you just do square root of x squared plus y squared?
So the whole idea is that you want to solve for y, because we want to determine if one x will lead to more than one y. So it's just handier to have it in a y equals format. You could certainly answer the question without doing that. Just plug in some x's and get some y's and see if you get more than one y. So if I make a little table of values now, if I plug in 0 for x, what do I get for y? Plus or minus 4, 1 input, 2 outputs, not a function. Okay, so we have to learn a whole special notation to deal with functions. So this table gives the height of a baseball, y, so that's what's on top is the height of the baseball, at various times x given in seconds. So the values listed represent a function because each time has a unique height of the baseball. You can't have one time in the baseball at 2 different heights. That would be mind-blowing, right? So this is definitely a function. So we say y is a function of x, and instead of using the variable y to represent the function, we tend to use f because it's the first letter of the word function, and then g and h because we're very creative when we just go to the next 2 letters in the alphabet. And then after that, we think that the letters are starting to get too far away, so sometimes we use capital F and capital G and capital H also to name the functions. This is how we name functions. Yeah. Sometimes we use other ones if we are being particularly creative. So we can represent this function by writing y equals f parentheses x. Okay. So this expression, f parentheses x, It does not mean f and x multiplied. It doesn't mean f times x. This is a repurposing an old notation to mean something new. And we read this notation as f of x, where the input is denoted by the x and the output is denoted by f of x. Okay, so x, this thing in parentheses here is your input, and f of x all together represents the output y. So some people like to say that f of x is a fancy way, oops, of writing y. So f of x equals would be a fancy way of writing y equals. And the x is just an input. Okay, the x is the x. F of x is the y. So here's my table again. So I'm going to evaluate the function f of x. So these are my f of x's, and these are my x's. So instead of calling that y, I'm going to call it f of x. And I want to evaluate f of 2. So this is asking us to find the output, that is the height of the baseball, when the input is 2 seconds. So the thing in parentheses always represents your input, and that's going to be time. So when time is 2 seconds, what's the height of the baseball? 99 feet. So f of 2 equals 99 is the notation we'd use. What is f of 0? 3. Oh, so I got to do these interprets. So this says the baseball is at 99 feet at time x. At time x equals 2 seconds. And f of 0 equals 3, what does that mean? Yep. At 0 seconds, that is right before we let go of it, right? Because we're throwing it up in the air. So right before you let go, it's 3 feet off the ground. So f of x equals 103. Now they've given us the output, right? So in the past ones, they were giving us inputs by putting them in parentheses and asking us to find the corresponding output. Now they've given us an output and are asking us what input gives that. So what x value gives a height of 103 feet? 2.5, and that's the only one, right? So this would be x equals 2.5 is the solution. And so we would say the ball reaches 103 feet at 2.5 seconds. So that's a table of values, right? We have a table of values for the height of the ball at various times. We could also use a formula that tells us the height of the ball at various times. So here's my formula, negative 16x squared plus 80x plus 3. And instead of writing y equals, I wrote f of x equals. So I'm using this new notation, fancy way of writing a y. So I want to use the equation now instead of the table to evaluate f of 2. F of 2. That means x is 2. I'm going to plug in a 2 into the formula. So I'm going to replace all my x's with 2's. And I get, so that's negative 64 plus 160. What is that? I should probably just get my calculator out. Negative 16 times 4 is negative 64. And then I want to add 160. 96 plus 3 is 99. 99. Which is the same thing I got above, right? 99 feet. All right, if I want to use the equation to solve f of x equals 99, so now I'm going to replace, if f of x equals 99, I'm going to make a substitution, right? F of x and 99 are the same, so I can substitute 99 for f of x in the equation. So I have 99 equals negative 16x squared plus 80x plus 3. And how would I solve this equation? Subtract the 99, so I have 0 equals negative 16x squared plus 80x, and 3 minus 99 is negative 96. And then you would solve that how? Quadratic formula, or you could play around with it and see if it factors. Let's use a quadratic formula. So I have negative b, that would be negative 80. Plus or minus, so I'll just do the plus first, because you have to do it separately in your calculator. Plus the square root of b squared, that's 80 squared, minus 4 times a, which is negative 16, times c, which is negative 96. And I should put parentheses around this whole thing. So that's negative b plus the square root of b squared minus 4ac. And I'll do all over 2a, 2 times negative 16. And I get 2. And I should do the minus also. So I press second enter, go up and change my plus to a minus. And I get 3. So I get x equals 2 and x equals 3 are my two solutions. So let's go up to the table. And when I look at 99, I look for 99. When do I reach that height? At 2 and 3. Height of 99 happens at time 2 and time 3. And yeah, right, good. That does agree with what we did earlier. The graph of a function can be found by plotting values, ordered pairs, x, y, that are solutions to the equation. Okay, so I just plotted y equals, or f of x equals, negative 16x squared plus 80x plus 3 in a program like GeoGebra. And I want to evaluate f of 4. So this is my x, and this is my f of x axis. So when I want to evaluate f of 4, anytime you have something in parentheses, that's an input or an x, right? So I find 4 along my x-axis, which I can't read this at all. Can they read yours? Okay. Hold on.